Okay, let's continue. My name is Sophia Scher and I work at the Donner Institute and I'm a member of the organizing committee of Aboagora. It's now time for our first Agora and I'm very happy to introduce Professor Andrew Coates. Coates is Professor of Physics and Deputy Director of the Mollard Space Science Laboratory at University College London. He has a Bachelor of Science in Physics from the University of Manchester Institute of Science and Technology and a Master of Science and a Doctor's degree in Plasma Physics from Oxford University. Professor Coates' scientific expertise includes plasma and its intersections with planets, comets and moons in the solar system and studies of planetary surfaces. And he has been involved in many space exploration missions with key roles in instrumentation. Public outreach and engagement is important for Professor Coates, as he feels that the general public should be involved in the excitement of space exploration. And we will now take part of Professor Coates' pre-recorded presentation on winds in our solar system. And after the presentation, he will join us online for a question and answer session.
Hi, I'm Andrew Coates from UCL's Mullard Space Science Laboratory, and it's a pleasure to talk to you today about winds in our solar system in this wind symposium. So in the background there's an image of the planet Neptune, and the reason for putting this in is that it has the highest wind speed, real wind speed of an object in the solar system, so a planet in the solar system. We're going to talk actually about two different types of winds. There's the solar wind, and then there's the real wind on planets, the winds in atmospheres. So we'll cover both of those today, and we'll also listen to some sounds of winds as well, which I think is really in keeping with the wind nature of the symposium. So just to start off, I'll sort of say a number of objects, planets in the solar system have got atmospheres. And there's some images of them here, and in case you don't recognize some of them, there's a look-up table here. So in the middle, we have at the top we have the Earth, of course, the blue object there. Then on the left hand, on the right, we have Venus and Mars. In the middle row, there's Jupiter, Saturn, and Titan. So Jupiter and Saturn, gas giants. Titan, a moon of Saturn. And then Uranus and Neptune on the bottom row, and in between those Triton, which is one of the moons of Neptune, and then Pluto. So all of these have winds, and we're going to be talking about quite a few of these and the winds in these atmospheres as we go through the talk. So we're going to start off, though, with the solar wind, and this is an image from the ESA-NASA Solar Orbiter spacecraft, which in February sent back this amazing image of the largest prominence coming away from the sun. So the image you can see actually is taken in the ultraviolet, and you can see some of the activity of the sun. The sun goes from low activity to high activity in an 11-year cycle. And we see this prominence here, very large. This can be the source of some of the impulsive events in the solar wind which we have going through the solar system. So the solar wind streams out from the sun. It's about 1 million tons per second, and it moves at 1 to 2 million miles an hour. So very fast wind in the solar system, and that interacts with the different planets and other objects getting in its way. So we're going to be talking about the solar wind and how that works as well. And actually, to start off with that, the sun, our sun is a magnetic star, and you can see that with these eclipse images, which again are quite beautiful. So we have, this is where the moon comes in between the sun and us, and so that blocks out the bright part of the solar atmosphere, and actually it reveals the solar corona, which you can see there. And this is behaving magnetically, so it's a bit like an iron filings experiment at school, you know, where you're looking at a magnetic field around a bar magnet. And these particular images on the top left is taken near solar minimum of activity, and on the bottom right, that's taken towards solar maximum. So the bar magnet with the open magnetic field lines at the top and bottom there, you can see on the left-hand image. Then on the bottom right, it looks a bit more complicated as we head towards solar maximum. Okay, so that's some, again, beautiful pictures of the solar corona. There's lots of things we don't understand about the sun. For example, why is the solar corona so hot? But one of the things that the solar wind has an effect, which you can see, and this is one of the two visible manifestations of the solar wind, is the aurora. So the northern lights and southern lights. Of course, you see the aurora, the northern lights sometimes in Finland when it's dark enough. And so visitfinland.com shows these amazing images of the aurora. So this is what happens when particles from space, which interact via magnetic reconnection between the solar wind and the magnetosphere of the Earth, so the magnetic field of the Earth. That happens both on the sun, the day side, and the night side of the Earth. Particles get shot from that towards the Earth, and when they hit the atmosphere, this is ions and electrons moving at high speeds. So you get this glow associated with the atmosphere, and so our oxygen and nitrogen atmosphere reveals this this greenish and sometimes red glow, which you get, and of course a very dynamic picture. This is just a still. So the aurora is one of the things which allows you to see that the solar wind is having an effect. On Jupiter and other planets which are magnetized, you also have an aurora effect. So this beautiful image of Jupiter on the left-hand side, showing the winds and the zones and belts, we'll get to that a bit later. But towards the North Pole here, we can see the aurora. And so this is taken in ultraviolet light. So this again is the interaction of ions and electrons from space, which are hitting the atmosphere. And in this case, it's a hydrogen and helium atmosphere, and it's mainly the hydrogen which is doing the emission here. So this is converted from the ultraviolet to something which we can see, which is the blue light. There's also this dot here. This dot is associated with Io, which is one of the moons of Jupiter, orbiting relatively close to the planet, but it is producing large amount, about a tonne per second, of sulfur and sulfur dioxide, which goes into the atmosphere and near region of Jupiter. And there's a magnetic connection all the way back to the atmosphere, and the foot of that magnetic field is actually here at this this beginning of this trail here. So this trail is to do with this material which is being added into Jupiter's system. There's also similar trails associated with the moons Europa and with Ganymede. Which are less visible, but this is sort of showing some of the features which are happening in Jupiter's environment. So the solar wind is interacting. Most of this is coming actually from inside the magnetosphere of Jupiter, but the solar wind is having some effects as well. At Saturn on the right-hand side, so these beautiful images from the time of the Cassini mission, when that was getting close to Saturn. This shows the 3 different images of Saturn on 3 different days, and you can see the aurora is behaving differently on these 3 days. So we had an instrument on the Cassini spacecraft, the orbiter, which eventually orbited Saturn. This was on the way going into orbit, and we measured changes in the solar wind, which we could then relate to these changes in the aurora. So that's quite amazing. We'll also see the Huygens probe, which landed on Titan, one of Saturn's moons. We'll see some information from that later, but this is the solar wind and how it's interacting with Saturn. So all of the planets with a magnetic field are having auroral type effects, so effectively the atmosphere being lit up by things which have originated in the solar wind or in the magnetosphere actually hitting the atmosphere. And this also happens at Mars as well. So this is from the UAE mission, which arrived last year at Mars, called HOPE. So Mars doesn't have a global magnetic field, but it does have crustal magnetic fields. And so these beautiful images here are to do with the crustal fields and how you get local particles, electrons mainly, hitting the atmosphere again, the relatively low pressure atmosphere of Mars, but producing the glow. And so this is being imaged for the first time really with the UAE mission. So some really nice images. And again, these are crustal magnetic fields, much more smaller scale than associated with those magnetized planets. So the next image just shows how the magnetized objects, like the Earth, interact with the solar wind. So the solar wind in this picture is coming in from the left-hand side with each of these objects. So if we start with the Earth is relatively small in this picture. This is the magnetic field associated with the Earth, pushed in on the day side and pulled out into a tail on the night side. And then Upstream of that is something called the bow shock. So this is happening to warn really the solar wind which is coming in, which is supersonic, of the obstacle, the magnetic field of the Earth in this case, in the background. So this is a bit like the bow shock around, or the shock around the supersonic aircraft. So you get a sonic boom associated with that. And the other objects, the other magnetized objects, do a similar thing and have a bow shock as well. So Mercury here on a much smaller scale. Uranus and Neptune on a much larger scale, and actually Uranus is really interesting because its spin axis is tipped. It's more or less in the plane of the rest of the planets, and so you can see that also the magnetic field of Uranus is at an angle to the spin axis, and so that means the magnetosphere is very interesting. And then on a much larger scale still, we have the Saturn and Jupiter magnetospheres, and each of these objects has a bow shock associated with them, as do the unmagnetized objects. And so on the right-hand side here, we see Venus, Mars, which we mentioned. It just has those small crustal fields, which are not affecting things very much, but they do cause those local auroral features. And then Pluto, now an ice dwarf planet, not an actual planet. And then the comets here also interact with the solar wind, and that's the other visible manifestation of the solar wind as it interacts with other objects in the solar system. So the Earth and all the other planets are bathed in the solar wind. So what happens when you get far away from the sun, as the Voyagers have done? So the Voyager spacecraft are over 100 times the Earth-Sun distance away, and they have actually left the immediate solar wind environment. In fact, on this image here, you see this is where the planets are actually sort of well inside this. This is the termination shock and then the heliopause. And actually both Voyager spacecraft are out in interstellar space now. And so they left in 1982 and in 2012 and 2018. So what we're going to listen to now is the Voyager mission had a plasma wave instrument on board, and once it actually got out of the heliosphere, it was able to capture some of the sounds of interplanetary space. So those intensifications which you heard are to do with the interplanetary medium. I think that's amazing to be able to hear via the plasma wave instrument what is happening in interstellar space, and so sort of slightly haunting sound which you get there. Okay, so on to real winds on real planets, and so Mercury doesn't really have an atmosphere, only has a very thin, tenuous exosphere, and doesn't have winds on it. But so the first planet with winds actually is Venus, and so if you're on a spacecraft, or if you have a spacecraft going close to Venus, as the Japanese did with the Akatsuki spacecraft, this is the type of image you get. So this V-shape in the clouds, and I should say these clouds are made of sulfuric acid. The surface of Venus is very hot. A runaway greenhouse effect has occurred there. It has a very thick atmosphere, clouds of sulfuric acid, but you get these V-shapes in the clouds. That's because the planet rotates very slowly in 243 Earth days. The atmosphere, as I say, of Venus is very dense. The atmosphere is super rotating, so it's moving over the surface more quickly than the surface is rotating, and so it's super rotating, and the speed of about 110 meters per second, and so that gives you these V-shapes in the clouds at Venus. So some interesting winds in an interesting atmosphere on Venus. We also have a vortex associated with each of the two poles on Venus, so a very different world to the Earth and inside of us in our orbit. So onto the Earth, and of course this is the blue marble picture from the Apollo mission. You can make out Africa here, and we have water in the ice caps, also in the atmosphere in the form of clouds, and of course in the ocean in the form of the blue coloration here, and of course that's why this is called the blue marble picture. And I think this is really inspiring picture, of course, and it enables us to see some of the wind patterns which we have on Earth associated with the clouds, which are water vapor clouds in our case. And actually, the Earth has quite complicated set of cells associated with the heating. So all winds are driven by a difference in temperature and a difference in pressure. So you have a high temperature to a low temperature and a high pressure to a low pressure. This drives winds. And we have these cells associated with the Earth, the rotation of the Earth, relatively fast, and it adds to some of this, which provides the wind patterns which we actually see. Then every now and then this pattern is disturbed by something like a hurricane which comes through. So Hurricane Ida, for example, in 2021 had a wind speed of 155 miles an hour, and that's what we can see on this image. So the Earth, of course, does indeed have winds, and we're very well aware of that ourselves. Also in the Earth's environment, associated with the solar wind, that's the magnetic field of the Earth is pushed in, and so we get the magnetosphere. And so the magnetic field lines, actually, which some of them are inside the magnetosphere. And if you get a lightning strike at one end, that can drive whistler waves, as they're called, to go from one hemisphere to another. You can sometimes hear this on AM radios. So we'll just play the sound associated with the whistler waves here.
Earth whistlers.
So you get the idea with that. So whistler waves, called that because they sound a little bit like whistles in the atmosphere. And of course, as I say, AM radios tend to have this sort of interference. But that is another sound of the Earth's environment. Okay, so the next planet out is Mars. And so Mars has an atmospheric pressure which is less than 1% of the Earth's atmospheric pressure. We have magnetic fields, as I say, these crustal fields, which are remnants of a global magnetic field which Mars once had, but it lost it 3.8 billion years ago. And since then, the atmosphere has been leaking away to space, and the atmospheric pressure is now less than 1% of the Earth's atmospheric pressure. It's a carbon dioxide-rich atmosphere. The ice caps here seasonally change. So as Mars goes round in its orbit around the Sun, which takes about 2 Earth years, that gives Mars its seasons, and so you can get heating of one or the other ice caps, and again a change in temperature, change in pressure, which drives a wind, which provides a cell of winds on Mars. So that seasonal exchange drives some winds. Occasionally on Mars, at a particular point around its orbit, we may get dust storms. So some of these can go global. And the image on the right-hand side here shows what happens during a global dust storm. The surface is just about, you can't see it very well, just about hidden. And so these dust storms, that is not a good time to be landing a rover. So we're sending a rover, Rosalind Franklin, in a few years' time to Mars, and we don't want to land during a dust storm, and so we will make sure we keep it away from that type of season. And of course other rovers are on the surface as well, and we'll talk about those in a moment. In fact, one of them took this image of local winds on Mars. So local winds can drive these dust devils. So it's a little bit like the dust devils you get between buildings on Earth or out in deserts where dust can be lifted into the atmosphere, and you get the same thing on Mars. And so this is rovers, the Curiosity rover, showing that local effect of the wind on Mars, the dust devil activity. Okay, so this little video is going to tell you about some of the sounds on Mars. So the Perseverance rover, this is an artist's impression of the Perseverance rover, which is on Mars now, and making some amazing measurements. In fact, eventually samples will be brought back from the surface of Mars associated with this rover, but it was able to take some sound on Mars as well. So I'll just play this video clip which goes into that. Okay, so I think that's pretty amazing to actually hear sounds on Mars. So some of them associated with the spacecraft, but you could hear the wind in the background, which, wind on an alien world, and the idea of hearing these sounds. I think there's something beautiful in the sort of art and science area about that, which I'm sure more could be made of, actually. Okay, so on in our exploration out to Jupiter. So that's the next planet out, and we can see here on this image are zones and belts in the Jupiter atmosphere. These are counter-rotating, so you can see some going one way, some going the other. There's weather systems, there's the Great Red Spot, so this is a very long-lived anticyclone weather system in the atmosphere here. In fact, that's been there since we first had telescopes in the early 1600s. So that was first seen then, so a very long-lived singularity of the winds in the atmosphere. So Jupiter is a gas giant, so it's mainly hydrogen and helium in the atmosphere, as I said, and then. So this is all flow in the gas, and so winds are producing this. The maximum speed near the equator about 150 meters per second. And this, in an art science symposium, is really one of the images to show. So this is from the Cassini spacecraft, actually, which was on its way to Saturn. We had a little instrument on board that, which I'll get to in a minute. But this is from the imager, and it shows some of the amazing detail in Jupiter's atmosphere in the background, and also little Io in the foreground. And so that is the source of that tonne per second of sulfurous material which goes into the atmosphere or the near environment of Jupiter. And again, beautiful picture showing a combination between a moon and then these atmospheric features behind, all driven by wind. So this is one of my favorite pictures from space exploration. Okay, some interesting analysis near the poles of Jupiter. So this is using a ground-based telescope to look at ALMA. So this is one of the ground-based telescopes, and this is looking at the aftermath of the Schumacher-Levy 9 comet collision, which happened quite a few years ago now. But the analysis showed 900 miles an hour winds actually in the towards the poles of Jupiter. Another thing you get towards the poles of Jupiter is some beautiful imagery as well. So this is taken by the Juno mission, which is arrived at Jupiter relatively recently, and this is a picture over the South Pole in each case. And on the edges, you see the sort of zones and belts which we were seeing in the Jupiter picture before. But this is now revealing new detail about what's happening at the poles. So we can see these big hurricane features, for example, near the poles, which are quite outstanding and beautiful, really. Okay, so another thing you can do at Jupiter is listen to its bow shock. So the bow shock of Jupiter is a little bit like the bow shock of Earth, and we can listen to the sound of that now.
Jovian bow shock.
And this is done by converting, again, the plasma wave data into what sounds like tweeting in the background, but this is actually upstream wave near the Jupiter bow shock. So you get this high-pitched activity in the plasma waves. The frequency is converted so we can hear it. And then we're approaching the bow shock. The upstream waves change a bit. Okay, so that whooshing sound is what you get basically when the plasma heats and slows, and so the plasma waves, the nature of them change, and you get that different sound. So there's something quite amazing, I think, about listening to other planets' bow shocks, and Jupiter's one is one of the largest. Okay, Saturn is the next planet out. So of course this is the one with the rings. This particular image is taken from the Cassini mission, which was able to go out of the plane of the ecliptic, and that again something a little bit like Juno is doing at Jupiter. So this allows us to see, for example, the shadow falling on the rings, and we can start seeing effects at the poles as well. The equatorial wind speeds at Saturn are larger than they are at Jupiter even, and so these are 1100 miles an hour now. And then if we look closer at the polar region, we get a beautiful effect. And so this is the hexagon, which is seen in Jupiter's and in Saturn's polar region. So this is to do with jet streams. We saw some jet streams on that image associated with the Earth before, the cells and so on. There are jet streams on that image, and these are jet streams we think at Jupiter. This was first found with the Voyager mission and then imaged in more detail with Cassini. There's a hurricane at the middle of this, which is something like 50 times the size of a terrestrial hurricane, and again some beautiful imagery. And in fact, another way of looking at this is shown here. So using different wavelengths, you can combine these in different waves to get beautiful imagery. And I think this is just a stunning image of this hexagon in the Saturn atmosphere. And there are 200-mile-an-hour winds in these regions, and this happens at the north and south poles. Okay, also in Saturn's atmosphere we have great white spots which occur from time to time. So unlike the red spots at Jupiter, these are much more seasonal, happening every 30 or so Earth years. It takes Saturn 30 years to get round the Sun, so that's its year, 30 years. And so every now and then you do get a white spot. So this happened early, and in fact during the Cassini mission while it was at Saturn, so it enabled the Cassini mission to actually image it. So you can see some of the amazing images here, some later images that show this completely encircling the planet. So again, some very large winds producing this, and I just think these are beautiful images. So the Saturn bow shock is another thing we can listen to, and actually Saturn has a higher Mach number, so stronger shock than we have even at Jupiter. So we can listen to the sound of that as well. So that's a stronger bow shock happening at Saturn. I think, again, it's amazing to be able to listen to the sounds of these different effects. Okay, so then we have Titan. So Titan, one of the moons of Saturn, and the Cassini-Huygens mission, of course, was to Saturn and Titan, and Huygens actually landed on Titan. This little video shows you about that and some of the imagery that it took on the way down to Titan. So an amazing set of images from the Huygens probe landing on the surface of Titan, and that's a European Space Agency probe. The orbiter, of course, is NASA's Cassini mission. So it wasn't only taking images which showed this alien world, and of course this is being carved by liquid methane and ethane, and has done over quite a long time, and that's what gives us the shapes there. And in fact, on the right-hand side here, we see an image taken from the Cassini spacecraft of Titan. This is a combination of images combining the infrared, ultraviolet, and the visible parts of the electromagnetic spectrum, so slightly different energies of electromagnetic waves. We can actually see down through the haze of Titan to the surface of Titan, and so that gives context for where Huygens actually landed. But as Huygens descended, it was able again to detect some sounds, and so we can listen to those now. And so this is amazing. This is an alien wind, really alien wind, a nitrogen and methane atmosphere, and the spacecraft is going down through those and being buffeted by this alien atmosphere at the same time. So we'll just play this sound. So it gives you an idea. You can hear the wind as you go down. Again, that alien atmosphere is going down through that. And actually, with our instrument, we were able to really found that there's prebiotic chemistry going on at Titan. So Titan's atmosphere, as I say, is alien. Titan is the only moon in the solar system with a significant atmosphere, and it's a nitrogen and methane atmosphere, very reminiscent of the early Earth's atmosphere. And that's interacted on by sunlight and energetic particles. And we produce actually prebiotic chemistry, and actually what we detected was very high mass negative ions, and there's a combination of negative ions, positive ions, and neutrals. This ends up drifting down into the atmosphere and causing dunes on the surface of Titan. Some of it goes down into the lakes and makes the haze of Titan. So this is where the space physics is really affecting what is going on underneath. And this was a discovery with our electron spectrometer on the Cassini spacecraft. Some amazing results. And as I say, it's a really alien atmosphere. Okay, so onwards and outwards to Uranus. So this is the one with the spin axis tipped over. So Voyager, when it passed, was able to see the rings and the orbits of the satellites, which come out perpendicular to that. So as it was flying past here, but not much effect in the atmosphere. So unlike Jupiter and Saturn, not much in the way of features which you could really analyze in detail. So you have to do some image enhancement. So if you do that, you can actually see Uranus clouds in the atmosphere, and then use those to start measuring winds. So here's some images in the infrared. That's another way of doing it, to actually use the infrared and peer through the atmosphere again and get some of these features in Uranus's atmosphere. But these are not there in the visible spectrum. But it allows you to measure wind speeds, and in this case up to 560 miles an hour. So again, getting quite high speeds. Okay, another way of analysing it is with ground-based telescopes. So this one is taken with the Keck telescope, and again you can see the tipped axis. These are the equatorial regions here, and then looking towards the poles. Again, we have that complicated structure, a little bit like Jupiter. So there's more analysis to be done there. But again, all this is caused by winds. Again, that basic difference between temperatures and pressures, which are driving winds. So on to Neptune. So we saw this at the beginning. So this is the highest speeds in the solar system of winds, wind speed up to 1,600 miles an hour towards the equator. At the time of the Voyager encounter, when this image was taken, there was a great dark spot that's disappeared. And in fact, Neptune's spots do disappear. Here's some examples here, where one of the spots is just disappearing. You don't see it eventually in the final images. But again, huge wind speeds which are being shown there. Okay, then on to comets, and comets are very interesting objects in the solar system. And as I said, comet tails provide the other way that you can actually see the solar wind and its effects. And in fact, comet or the solar wind was originally discovered by looking at comet tails. So here's an image on the left-hand side of a comet. This particular one is a really bright comet, Hale-Bopp, which was around a few years ago now. But we can see two different types of tails. This white tail, which is the dust tail, that's dust being driven away from the sun, coming away from the comet. So the comet, as it comes towards the sun, the water starts subliming evaporating off the cometary nucleus, taking dust with it from the surface, and so that dust gets driven out by the solar radiation pressure, and eventually it reflects sunlight, and that's what you can see, this sort of white tail here. The blue tail on the left, this is pointing more away from the sun, and actually this is the plasma tail. So this is to do with the solar wind, and the solar wind is pushing the plasma away, and actually the plasma tail just about always is almost exactly anti-sunward in its motion, and that's what we can see here in this artist's impression of a comet, what happens with the comet as the comet goes around the sun. So you get the increase of activity, the formation of both the dust tail, which is the curved one here, and the plasma tail, which points away from the sun, almost exactly apart from the comet speed around the sun, and then dies away again. On the right-hand side, this is an image from the Rosetta mission. So the Rosetta mission visited Comet 67b, Churyumov-Gerasimenko. This is about a 4-kilometer nucleus. We can see that's got 2 lobes to it, like many other comets which we've visited. And you have the active material, the dust being pulled off by this subliming water. And you can actually see that reflecting there. So it's a close-up picture of what is happening in the nucleus region there. Because Rosetta was orbiting very close to the cometary nucleus, and it actually flew with the comet as the comet came into the inner solar system, activity developed and so on, and then into the outer solar system again. And actually it had a little lander called Philae, which landed on the surface actually 3 times. It bounced on the surface, didn't hold correctly, but nevertheless was able to sample 3 different locations, and eventually came to rest. And once the batteries unfortunately ran out of power, we didn't get more information from it. But there were some very interesting results from that, which showed some of the fundamental composition of comets. And in fact, one of the things which happened with Rosetta, it had a magnetometer on board the orbiter, and one of the things with that is we could actually hear the interaction of the comet with the solar wind. So bear in mind, this is very close to the comet. You have particles which are coming away from the comet, being interacted with by the solar wind, and then we have this singing comet idea. So what's happened here is the magnetometer, magnetic field results have been. That is sensitive to very low frequencies. That has been increased by a factor 10,000 here, so we can actually hear it. And this is related to the cometary activity. So we will have a listen to the singing comet. So it's quite beautiful in itself, and we're not 100% sure exactly what is causing the change in pitches and so on, but this is interesting and something from an actual comet. So I thought this was nice to share with you. Okay, with that continuing in the background, we can actually now go on to extrasolar planets, and so there are also winds here. Now we can't image extrasolar planets yet. The image on the right is an artist's impression. But the Hubble Space Telescope did actually take some spectra from here. It shows it's basically a bluish colour. And the artist has kind of added onto that the fact that we actually find there are very large high-speed winds. This is an object which is relatively close to its parent star, and we have winds which are over 5,000 miles an hour. And the atmosphere here, we know there's silicate in the atmosphere from some of the analysis which has been done. So what could be happening on this object is it may be raining glass sideways. So really not something to visit. I mean, it is 60 odd light years away, so we're not going to be visiting it. But nevertheless, I thought it was quite interesting to put in because it has such high speeds associated with the atmosphere here. Okay, so just heading towards the end here. So this is just a summary of the different objects we've looked at in the solar system and indeed the solar wind, looking at the wind speeds associated with this, both in meters per second and in miles per hour, because I've used a sort of mixture of those. If you look at the miles per hour, for example, so we're changing from relatively low speeds. I mean, Earth has some quite high speed winds, but then in the solar system itself, Neptune has the sort of record for wind speeds, but then this extrasolar planet has 5,000 mile an hour winds. But in the case of the solar wind, it may be 1 to 2 million miles per hour. So the solar wind is the winner in terms of wind speed. And of course, other extrasolar planets will have their own planetary solar winds as well, or stellar winds, which they're immersed in. Okay, so could we breathe these atmospheres? So no, apart from the Earth, of course, we can breathe the Earth's atmosphere, and in fact, Earth is the only place we know at the moment where there is life in the universe, and so we're looking for signs of life elsewhere in the solar system. So we have the Rosalind Franklin rover going to Mars in a few years' time. Perseverance is already there. We're going to be bringing samples back to analyse on Earth. But Rosalind Franklin is going to be drilling 2 meters, so that's going to be really doing an important job to do that. So I'm principal investigator for the camera system on that, the PanCam, which will be helping us to decide where to drill. The other atmosphere is very interesting, as we've talked about. We couldn't breathe any of them, and we're looking for life elsewhere. So Mars, but also moons like Europa and Enceladus, and eventually Titan, perhaps. There's prebiotic chemistry going on there. So these are very interesting objects to look at. So just to finish, we've looked at some really remarkable atmospheres, both in the solar system and beyond. The Earth, of course, is the only place we can breathe, but the search is on for habitability and life elsewhere. So Mars, Europa, Enceladus, and Titan. And there are future missions associated with those. But winds are always a key feature of atmospheres, and they're always driven by differences in pressure and temperature, so high pressure to low pressure, or high temperature to low temperature. That's the binding thing between them. And we've been able to hear in this talk winds on alien worlds at Mars and Titan. There are recordings at Venus as well, but there's also effects of the solar wind. We've listened to those at Earth, Jupiter and Saturn. So I'd like to thank you for listening very much, and see if there are any questions. Thank you.
Thank you so much. I think we have Professor Coates with us now. And we have time for a few questions, so I'll just reach out to you. Who wants to start? We're all dazzled by the winds, I think. But I just heard there was some really new images coming out now from, I think it was Jupiter. Could you tell us a bit more about that?
Yes, so this week actually, the JWST, the new space telescope from NASA, released some new images of Jupiter. So I can actually try and share those if you like. And let's see if this works. So hopefully you can see that.
Yes, we can.
So this first this first image here. It's from the JWST. So the JWST is a new space telescope. It works in the infrared part of the spectrum, so it's not visible light. But for this, it's been converted to visible, and 3 of the filters working at particular wavelengths in the infrared have been used to enhance what we're seeing. So this is a really, one of the first tests of the amazing new JWST. So we can see Jupiter there, the great red spot, which I mentioned in the presentation, the zones and belts, beautiful looking, and you can also see the aurora at the northern and southern poles of Jupiter there. So some really nice new images this week, which literally just released in the last day or two. And these are quite interesting because it's an infrared telescope, as I say. It's at the L2 position behind the Earth, looking at the sky, mainly looking at galaxies and distant events going on in the universe, but also it can be trained on solar system objects, as we can see. And it's an interesting image because this one, the help actually of an amateur astronomer an amateur astronomer actually helped to enhance these images. So, of course, there's a professional team working on it, but producing these amazing images. Judy Schmidt actually helped to do that. The second image here, that again shows Jupiter with this amazing detail. You can also begin to see the rings of Jupiter and some of the moons. And actually there's an annotated version of the picture here where you can see the northern aurora, the southern aurora, a couple of the moons there which are turning up, not the large moons, but you can certainly see the rings of Jupiter as well. So it's just really nice to see that the JWST is working very well and really promises very well for the future. So it was launched, of course, on Christmas Day last year and is now up and running and should be able to throw more light on the universe and indeed the solar system. So I just thought it'd be nice to show those because that's a relatively new set of images which thought it'd be interesting to share with you.
Yes, thank you. Any questions now? Yes, we have one in the back.
Hi, thank you for the nice presentation. It was quite informative and kind of complete about solar system. I have a question about the audio you played from Voyagers. We know that sound travels within the material, so there should be some kind of material. And then Voyagers have detected these kind of vibrations. So I suppose that they went through some kind of gaseous material. Is it true?
Oh. It's a good question because actually what is being played there is the sound of plasma waves. So this is waves in the plasma, which is a very tenuous plasma. At the Earth's orbit, the solar wind is like a few particles per cubic centimetre. So if you imagine a cubic centimetre like that, the air in the room there would be about 10 to the power 19 particles per cubic centimetre. At the orbit of the Earth, it's a few particles per cubic centimetre. But out in interstellar space, where the Voyagers are, it's much, much smaller than that, a few more orders of magnitude down in terms of density. But what's happening is that waves are produced in the plasma. So it's slightly denser regions of plasma just upstream of the heliosphere, as we call it. That's the zone where the solar wind propagates. And of course, the Voyagers are outside of that. So it's really sort of tenuous material in interstellar space, but it's converted to sound, but from these plasma wave, different frequency types of vibrations. And the other sounds which I played also from the bow shocks of Jupiter and Saturn, again, those are plasma waves and converting those into sound. So it's not a real sound because, of course, space, as you know, there's the famous quote, "In space nobody can hear you scream," because there's virtually no material. However, the solar wind does provide a few particles, and so you do get these waves, but they're waves in the plasma, so a little bit different from the waves that we have, that I'm speaking to you with, for example, using sound waves. And then, of course, we have electromagnetic waves as well, which is doing the internet. But sound waves are in gases. If you have a plasma, you unleash the power of electric and magnetic fields to be able to produce different types of wave modes, and it's a fascinating topic in itself. But those waves from Voyager are from interstellar space, but they're the sounds of plasma waves. So I hope that answers the question.
Yeah, thank you.
Thank you very much. It's time for one more question, if you have one. Yes, over there.
I'd also like to say thanks for such a fascinating presentation about something I knew literally nothing about until an hour ago.
Thank you.
On the topic of the heliosphere, the influence of the solar wind in space. In the diagram you showed, there was kind of like a dark blue circle where the solar system was, and then this heliosphere, and it kind of stretched off into one direction and not the other direction where the Voyagers were. And I wondered why it's so like long on one direction and not the other.
Yeah, that's another great question. So of course, if you imagine the Earth in its Milky Way galaxy, we're about maybe 2/3 of the way out along a spiral arm in the galaxy, and so what we're seeing with Voyager and the solar wind is the relative motion of the gas in the spiral arm of the galaxy compared to the heliosphere and what we have, the solar wind, which is blowing outwards and producing this sort of bubble in space. So on one side we have the flow, relatively speed of the material in interstellar space, and on the other side, sort of pulled out into a tail. So it's a little bit like those diagrams I showed of the Earth's bow shock and the magnetosphere and so on. So this is happening on a huge scale with the entire heliosphere, and it's the interstellar medium, which consists of neutral gas and plasma, but very, very low densities. The composition of that is important and interesting, by the way, and we don't fully understand exactly what that is. There is work going on with Voyager and with other missions to do that. But yeah, what you're seeing is sort of being effectively pushed on the one side, which is happened to be the side that the Voyagers went out of, and pulled out into a tail on the other side. So it's a little bit like, on a huge scale, what's happening with the Earth and the other planetary magnetospheres, Saturn, Jupiter, and so on. Okay.
Thank you very much. I think this was a wonderful first Agora, really bringing us into wind, and we're going to continue with more. But now, again, a big thank you to Professor Coates.
Thank you very much, and thank you for inviting me.